All right, so I thought I would start this out. Let's get our calculators out if you have one. If you don't, you can use your phone, but make sure that that's all you're doing is calculations. So I have two problems to kind of introduce you to this topic, this idea of sequences and series. How many of you have to take Calculus 1? Okay. How many of you have to take Calculus 2? Oh, good. Okay, so maybe I'll see you down the road because I teach the calculus sequence most of the time. So in Cal 2, Chapter 8, it's called Sequences and Series, is the hardest chapter in the sequence of calculus, probably. I mean, if you look at Cal 1, Cal 2, and Cal 3, most people say Chapter 8, Sequences and Series, is the big trouble spot. This is just a very, very light, basic introduction. So this is in no way, shape, or form what you'll see. But the way I'm going to present it to you is with that in mind that later on you're going to need this for something. So let me ask you to think about two different concepts. So first concept is this. Which one should I start with? All right, let's start with this one. Let's say I have a container, all right? And let's say that this container holds precisely 1 cup, all right? And it's empty. And so what I'm going to do is I'm going to have another container filled with water or Kool-Aid or beer or whatever you want it to have. And I'm going to pour into this exactly 1/10 of a cup, all right? So imagine me pouring some liquid in there. So now I've got 1/10 of a cup in there, right? Then I'd like to come in here and pour in 1/100th of a cup into this. Water level's going to rise a little bit. Yes? Okay. And then after that, I'd like to pour in 1/1000th of a cup. Do you kind of see a pattern here? Yeah? So the water level's going to come up a little bit more. And I'm going to do this again, 1/10,000th of a cup. So I'm just adding a 0 to this every time, right? And I'm going to continue, and I'm going to do this forever. It means I'm never going to stop. And if I could do this forever, my question to you is whether or not this cup is going to overfill or not. So think about it for like 5 seconds. Imagine me doing this forever. So let's take a vote. Let's take a vote. Will we overfill the cup? Those are the people in favor. It is going to overfill the cup. Okay. And then the people who think that we will not overfill the cup. Okay. All right. So I would ask for some justification. So the people who think that it will overfill, anyone want to explain why they think it will overfill? Go ahead.
Well, you said if you keep doing that forever.
Forever, that's right.
So at a certain point, it's going to overflow. If
Okay.
you just keep doing it.
If you keep adding
liquid into a cup, eventually it's going to.
Even a drop at a time, it's eventually going to get to that last drop right over.
Okay.
I feel like though, depends on what atmosphere is in.
Okay, so yeah.
Evaporate and then obviously.
Okay, so there are some factors that we could put into it, like evaporation. Like, can you get to a point where these become so small that you're beyond like atoms? Let's throw that out. Okay, let's keep this purely theoretical. If it was possible to neglect evaporation and that we could go smaller and smaller without ever breaking into the atom, theoretically, purely theoretically, will it overfill? So you're going to stick with it? Okay. So you're still saying yes. Can I try and formulate your argument, help you formulate your argument? Okay. This is a finite cup. We all agree? Each one of these is a positive number. Yes? This is a positive number, a positive number, a positive number. So if I have a finite cup and I keep adding something to it, then I must overfill the cup. Is that a good argument? Am I kind of summarizing your point of view?
Yeah.
Okay. Now, oppose and oppose. You don't think it's not going to. You want to?
I'm just thinking almost like a graph. You know, if you have like 1 over x, no matter what you put in there, you're never gonna quite get. You know, you can get as close. You know, you can get real close to it.
Okay.
But you're never gonna cross that threshold.
So-
I'm feeling that's kind of in a theoretical situation. That's what you're basically gonna do.
Like some sort of asymptote almost,
Right.
where you're not going to get past a certain point.
Right.
Do you have?
Along the same lines, he worded it better than I would have. It's getting smaller and smaller and smaller. Yeah, eventually, I mean, you may get close to the edge of the cup, but then you factor in the evaporation and stuff.
But we're not doing evaporation
I know,
though.
I know, and that was my original.
You were thinking evaporation originally. Okay. Well, I don't know the answer actually. No, I'm kidding. I'm kidding. No. The thing that's good about this example is that you can have, this is where you have like intuition, you know, and you have like a certain feeling of you think this is going to work a certain way. And you can have debates back and forth about why you think your intuition is right and someone else's is wrong. But at some point we need to be able to fall back on something that's solid like mathematics. And so as you're going to see, the answer to this is going to go against a majority of your intuitions. All right? This is not going to overfill the cup. And there's a very simple way to show it, okay? I'm going to show it to you in a simple way. All right, so I'm going to convert each of these fractions to decimals. All right, so this right here is 1/10, and as a decimal, that's 0.1, right? Plus, this right here is 0.01, and this one is 0.001, and this one is 0.0001. You get the idea? All right, so let's just start adding these up. If I add these two together, I get 0.11, don't I? And then if I add the next one, I'm going to get 0.111. And then if I add the next one, I'm going to get 0.111. And then I keep doing that forever. I should get, like, if I could do this forever, right? This should be 0.111 forever. So a little bar on top. Agreed? Now, what is this? Well, it's 1/9. And if you don't believe it's 1/9, just go to your old school division, like how you would do this. This is 9 out here, 1 there. 9 doesn't go into 1, so you put a decimal and a 0. Now, bring your decimal up. 9 goes into 10 once. You'd bring your 9 down, subtract. You'd be left with 1, then drop your 0, and then 9 goes into 10 once, and then it would just keep doing that same thing over and over and over, and you just get 111 forever. So not only is this not going to overfill the cup, it's not even going to fill it up halfway. If you could do it forever, it would be exactly 1/9. If you ever stopped, so if you kept on doing this, if you ever stopped, you'd run a little short of 1/9. But if you could go forever, it would asymptotically approach 1/9. So I think this is a good example of how your intuition tells you one thing, but mathematically there's something else happening. So this right here is something plus something plus something plus something plus something, right? That's what we call a series. Okay, so you have a summation like this. This is called a series. And in Calculus 2, which a lot of you said you had to study or had to take, we study series and we talk about their behaviors, and certain series do certain things. Some of them go to a number like this. We call that convergence. Some of them do overfill. I mean, I think it'd be obvious if I said if I was going to take this and pour in half a cup, okay, and then half a cup, and then half a cup, like that's going to overfill, right? Half plus a half plus a half. That's a different series though, so it behaves differently. So we have all these different types of series, and what we're going to talk about here today are geometric series and arithmetic sequences and series, and we are not going to add forever. We are going to stop. So we're going to add to a certain point and stop and figure out what does it add up to be. Those are called finite series. In Calculus 2, you study infinite series. So you allow the process to continue forever. All right, that's the first kind of like topic introduction. The second one, oh yeah, your calculators. I couldn't remember what I was going to do. All right, are you all familiar with this function? You've seen this before, right? So we all know that as the exponential function. The natural exponential function, the base e is real special, right? We've been told it's like this awesome thing, and in calculus you'll see why it's so awesome. But in here we just kind of are told that it's going to be important later, right? All right, so if I asked you right now to tell me what f of 2 was, in other words, if I ask you to do e squared, you would go to your calculator, you type it in, right? So I'm going to type that in my calculator. And I'm going to get, my calculator is telling me that this is 7.389056099, and that's where my calculator stops. But it actually keeps going, okay? Yeah? So when I type that into my calculator, what did my calculator do? So how many of you are computer science majors? Any computer science? Okay, so what did I don't expect you to know the answer to this, okay? But I want you to think about it. Like, what did my calculator actually do in order to generate this answer? Because all a calculator can do is add, subtract, multiply, and divide. Now, it can do powers also, but it looks at powers as repeated multiplication. So like it looks at, 4 cubed as 4 times 4 times 4, right? That's what it looks like. So what's going on here? And later on when you take pre-cal, you'll discover that you'll discover these functions like the sine function, the cosine function, the tangent functions, these trigonometric functions that you study in pre-cal. And when you type like sine of 2 into your calculator, like what's happening, right? So let me tell you what's happening. In your calculator does not define e to the x this way. Your calculator actually defines e to the x to be 1 plus x squared over 2 plus x cubed over 2 times 3 plus x to the 4th over 2 times 3 times 4 plus x to the 5th times 2 times 3 times 4 times 5 plus x to the 6th. Are you seeing a pattern? Times 2 times 3 times 4 times 5 times 6 plus forever. Okay, so if I were to put this on the board right now, what type of function is this? Quadratic. And that would be the first 3, right? If I did this, that would be a linear function, wouldn't it? That's a line. This is a quadratic function. This is a cubic function. This is a 4th degree polynomial, 5th degree polynomial, 6th degree polynomial. You see this? Your calculator is actually looking at the e to the x function as a sum of powers of x. So it's like an infinite polynomial. Remember we just did 1/10 plus 1/100th, all that? And it was just a sum of a bunch of things? That's what I want you to see here. This is a series. Okay, this right here is what we call later on in calculus a power series. They call it a power series because notice that each term is a power of x. This is x to the first power. This is actually x to the 0. X to the 0, x to the 1, x to 2, 3, 4, 5, 6. So it's a series of powers of x called a power series. Every function that you will ever study in any class that you take below Calc 3, any function you ever look at will be able to be represented this way. And that's how your computers actually calculate it. So when I typed e squared into my calculator, here's what my calculator actually did. It did 1 plus, you replace that with a 2. 2 plus 2 squared is 4, 4 over 2, plus 2 cubed is 8, 8 over, 6? Plus, what are we at, 16 over 24 plus, and I'm going to stop there, but you get the idea? Now your calculator couldn't go forever. It had to stop somewhere. And that's already programmed into the calculator. Whoever, the software engineers that designed the brains of this thing, they predetermined where this would stop, all right? And if I'm going to do this on my calculator right now. I'm just going to go out to here. If I do 1 plus 2 plus, that's another 2, right? Plus 8/6 plus 16 over 24. If I stop there, well, that kind of sucks. Let me go one more. It's 7. That's not close enough. Let me go one more. So what would the next one be? This one right here? Be 32 over, I think, 120. There we go. If I stop there, it's 7.2666. Now, do you remember what the answer was when I did e squared? It was 7.389, so I'm still off, right? Well, all I have to do is keep going out a little further. If I go out further, I'll get closer and closer, and I will get the decimal close enough to where this spits out the answer, okay? So that's what's happening in your calculator. It's not some crazy E thing that the computer, knows what E is. It doesn't know what E is. It just knows that it's a power series, and it just computes the power series. All right, so all of that is just to get you kind of thinking about what series are, what they're useful for. And now let's start looking at this worksheet and see if we can't work through it, all right? By the way, that problem with the liquid, like the overfilling thing, whenever you have something that happens that goes against what you think, we call that a something like a problem that is non-intuitive. Non-intuitive. It goes against your intuition, right? And that happens quite a bit later on in math. You trust your gut, and then you go, oh, great, it's not right. You don't want to be an engineer building a bridge going, yeah, that looks strong enough. I think that'll hold, right? No, you got to trust the math. All right, so here we go. We are going to talk about arithmetic and geometric sequences and series. So what is a sequence? What is a series? Because they're two different things. So let me first try and define for you. Y'all have not talked about sequences or series at all, right? This is the first time you've ever seen it? Okay, so a sequence, I don't see a definition here. A sequence, by definition, is a list of numbers. That's it. It's a list of numbers. All right? Now, later on in math, you can have sequences that might be a list of functions or something like that. But for what we're doing today, we're going to say a sequence is a list of numbers. So I'll just list some numbers out here. 1, 2, 3, 4, 5, ... Let's stop at 15. That is a sequence of numbers, isn't it? Those are the counting numbers. That's an example of a sequence. Another sequence, -2, 0, 2, 4, 6, 8. Those are a sequence of numbers, right? Those are evens, aren't they? Those are a bunch of even numbers. Okay. Both of these lists of numbers are called finite sequences. I'm just go SEQ for sequence, all right? They're both finite, meaning that they started somewhere and stopped somewhere, right? If you wanted to have an infinite sequence, what you would do is this. 1, 2, 3, 4, 5. You do enough numbers to kind of establish the pattern, and then you put ... usually 3 dots. And that means continue that pattern forever. This would be the way you would write an infinite sequence. Understand the difference? Okay. We are going to be talking just about finite sequences today. There are all sorts of sequences out there. I mean, you can come up with any sequence you want. Just start listing numbers, and that's a sequence, right? But there are special ones. One of them is called the arithmetic. The other one is called the geometric. And those are the two that we're going to look at today. But while we're looking at them, have any of you ever seen this sequence before? I told Mrs. Manchester that it's going to be hard for me to stay on task today. Has anyone ever seen that sequence of numbers before?
1 times 1 is, or 1 plus 1 is 1, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on.
Okay, so like the next number here should be what?
5.
It should be these two added? So it looks like, yes, you found the pattern. The pattern is that if you pick a number in the sequence it is actually the sum of the previous two. Now, that doesn't work for the first ones because there's nothing in front of them. So you put 1 and you put 1, those are the start, and then from there on, 2 is those two added, right? 3 are those two added, 5 are those two added, 8 are those two. You see that? It's a very famous sequence if you've never seen it before. I might not spell this right. Fibonacci? I think that's misspelled. Who cares? It's the Fibonacci sequence, all right? That's a very famous sequence. It is associated with something called the golden spiral.
Finding things in nature.
Finding things in nature, yep. So you've seen something like this? You can, if you do this, if you draw a square, okay, see that square? I'm going to put a 1 in it, and that 1 means that each of the sides is 1 unit long, okay? So I'm going to put another square next to it. What number goes in there? 1, because it's the same, right? 1, so that goes 1. Now I'm going to draw this square. Tell me what I should put in that one. 2, because each length size 2, right? Now I'm going to put another one right here, 3. I'm going to put another one like this, 5, and then I'm going to put another one like this. Oh, wow, this is not looking good, but you get the idea, right? You see what's happening? 13. Okay, so now if I go and start at the very first one I drew, actually I'm going to start this one right here. If I connect this corner to this corner with a curve and continue that pattern, crossing each box with a curve, then I get what is called the golden spiral, which is found in nature in many different places. Can't quite understand why. But it's almost like, you've seen like a shell, like a seashell, you know, and the way the spiral is. I mean, there's different ways you can have spirals. Like I could draw a spiral like this, where my spiral almost has like the same gap between each spiral. But in nature, the spirals like start real tight and then they kind of widen out, and they follow a certain sort of ratio, and it turns out that it follows this ratio, and it's strange. We don't quite know the connection, but it's weird. Even the way like the DNA strands work and stuff, or even the way branches on a tree grow, it's all somehow connected to this weird. Anyway, okay, so that's another example of another sequence, all right? Got the Fibonacci sequence. But we are going to look at the two most basic sequences, and those are the arithmetic and the geometric. So look at the sheet that you have there, the arithmetic sequence. An arithmetic sequence, a sequence is called an arithmetic sequence if there is a constant d, called the common difference, such that a sub n minus a sub n minus 1 equals d. What the? Now, I'm not real, this handout's a little deceiving because there's capital A's mixed with lowercase a's. Everything in here should be a lowercase a. So if you see a capital A, it should be lowercase, all right? So let me try and explain what's going on here. That's what makes a sequence an arithmetic sequence. Arithmetic, think of the word arithmetic, okay? So this is what this is saying. Let's say you have a list of numbers. Let's see, just arbitrary numbers, right? This is going to be a sequence. Let me call the first one, I don't know, how about I call it a subscript 1? That's the first number in the sequence. Comma, the second number is a sub 2, right? The next one is a sub 3. The next one's a sub 4. And then I just have this sequence, and maybe it ends out here at a sub, I'll put n. That would be a finite sequence, wouldn't it? Whatever a sub 1 is, it's the first number. This is the second number, third number, fourth. To be an arithmetic sequence, you have to have this be true. Meaning that if I pick any number in the sequence, so let's say I pick a sub 4, then if I subtract from it a sub what? 3, right? If this is 4, then that's 4 minus 1, that's 3. If I subtract the 1 right in front of it, that I get some number out, and that number never changes. So there's always a common jump from one number to the next. Can anybody give me an example of an arithmetic sequence without cheating and looking? Make up their own? I'll start you out. I'll just give you 3 now. What?
I was kind of like 3, 6,
Okay, so 3, 6, 9, 12, 15. Would that be an arithmetic sequence? Now, I'm going to be tempted to keep doing ... because I think I'm in Cal 2 right now. I'm not in Cal 2, so I'm going to stop it somewhere. So why don't we stop at, I don't know, how about 30? Okay? That is a finite arithmetic sequence. Because if I pick any two in here and subtract the second one from the one in front of it, right? I'm going to get a common difference of 3. Right? The common difference will be 3, no matter where I start. Y'all following this or not?
Yes.
So common jump of 3 here, 3 here, 3 here. Not multiplying, but the difference, in adding of 3 each time. Okay, that's an example. Let's do one more. But let me start you out over here. Can you give me an arithmetic sequence that starts negative?
-6, -5.
Okay, you could do that. You could do that. -6, -5, -4, -3, right? And then maybe let's stop it at 100. Okay. So what's your common difference here?
1.
Just 1? What are we doing each time?
Adding one.
Adding. So that difference, that jump is 1, right? Now let's verify that. Let me pick one of these. Let me just pick one of these, -3. And let me subtract from it the one before it. So if I subtract the one before it, I'm subtracting -4. And when you subtract a negative, it really means plus. So this is -3 plus 4. So my common difference is 1. See that? Okay, so that's what makes arithmetic arithmetic. With me? Okay. So for these first 3 examples, what's the common difference on that first one? Can you answer that one? 2, right? Just jumps by 2 each time? Okay. How about the next one?
5.
5. And the last one?
1.
It's 1. How'd you get 1?
2 over 2.
What'd you do?
2 over 2.
2 over 2. Oh, so you just did the subtraction? Okay, so if you're having any trouble, which doesn't look like you are, I would just say for that last one, you pick one of them, like 3 halves, and then what's the one right before 3 halves?
1/2.
1/2, and you subtract the 2, and you get 2 over 2, which is 1, right? But see, to be arithmetic, that would have to hold for every pair. Every pair in the sequence would have to have a common difference of 1. All right. We good? Sure? Notice also on this formula, there is another way to write it, and that was, how did that formula come about? This says, hey, the common difference is D, and then they say, hey, but there's this other formula. So did they make up a brand new formula? Or
They just moved.
yeah, all they did was they just took this right here, moved it to the other side, and it became positive. And so it looks like a brand new formula. It's still the same thing, right? But what's cool about this one is that if you want to know what's happening, you know, at, let's say, the 7th one, right? If you want to know the value of the 7th term of the sequence, you just need to take the 6th one and add the common difference to it. So just a different way of doing the same thing, I guess. All right, arithmetic. That's what they look like. Now let's talk about geometric. Geometric sequences are still sequences, but instead of having a common difference between each one, they have a common ratio. So let me show you, well, they give you one here already, but I'll make up my own. 1, 2, 4, 8, 16, 32. Let's go out to 128. First of all, is that arithmetic? Is it arithmetic? Is there a common difference between each one? So to go from here to here, I had to jump by 1, right? But going from here to here, I had to jump by 2. It's not arithmetic. Arithmetic, you have to have the same jump in each one, right? So right away, I know this is not arithmetic. Now the question is it geometric? Well, to be geometric, the formula is this. that a sub n over a sub n minus 1 is equal to some constant r. Compare that to this. This was arithmetic, right? The difference between two of the terms had to be a constant. Geometric says the ratio of two consecutive terms has to be a constant. So totally different operation, right? Subtraction, division. So is this geometric? Well, let's take this one, 2, and divide it by 1. And we get 2, right? Now let's take this one, 4, and divide it by 2. And we get 2. Now let's take 8 and divide it by 4. You see what I'm doing? Do you all see what I'm doing? I'm just grabbing, like if you grab any one of these and then divide it by the one in front of it, are you going to get the same number every time you do it? Yes. So this appears to be geometric with r being what? 2. R is 2. So this is, I'm going to put geo, right? This is a geometric series, and r is 2. I can't help but bring this up. Do y'all recognize these numbers? Like 8, 16, 32, 64. They're all computer numbers, aren't they? Like, you all own phones. You all have iPhones, right? Who doesn't have an iPhone? I don't have an iPhone. I always take votes in my class, and it's always like me and like one or two other people don't have iPhones. So when you go get your phone, especially the iPhones, you have to pay attention to the memory, right? Like how much storage space you have, because you can't expand the memory, or you can't expand the storage. So don't they always sell these phones, and it's always like, this one has 16 gigs, or 32 gigs. Like, why is it never 40 gig? You know what I'm saying? Why do they always go by these increments of 8, 16, 32? Does anyone know why?
The data bus is only 8.
Okay. You're tying into the right thing. It has to do with computers.
Byte is one piece of bit is 8. So I mean, everything's a multiple.
So what does a computer know? At the end of the day, a computer simply is interpreting electrical signals as either being there or not being there. It's either on or off. Everything is a switch for a computer. It's either on or off, right? That means there's only two states that you could possibly have. And we represent those two states in a computer as 0 and 1. Zeros and ones. So a computer only knows zeros and ones. So everything is what we call binary. 0, 1. Binary number system. The binary number system is base 2, which means everything has to be a power of 2 in a computer, which is why these numbers are always the ones you hear. You're never going to get a computer with, or a phone with 122 gig. It's always going to be 128, and then the next jump up will be by a factor of 2, up to 256, right? Okay, that's just random useless information. All right, so that's a geometric. Let's look at some of these other ones. So what about this one here? 1, 3, 9, 27, 81. Yeah, that's geometric. Common ratio is 3. 3 over 1, 3. 9 over 3, 3. 27 over 9, 3. 81 over 27, 3. We good? Okay, and then the next one just looks weird.
-4.
Yeah, it looks like we have a common ratio of -4. But what's cool about this one is this is the first sequence that we've actually seen where your signs are alternating. Right? You've got like a negative, then a positive, then a negative, then a... We actually call these alternating sequences. It's not in here. It's not for this class, but that's what we call them. But if I take this over this, I get -4. But this over this is also -4. This over this is also -4. So we got our common ratio of -4. What about that last one? Is it 1/3? So let's just double check our math here. If we do -4/9 and we divide it by -4/3, you need to make sure you're comfortable dividing a fraction by a fraction. So how do you do it? I'm not sure how you do it. What? You flip it? Okay, so you just take this one, flip it up, and multiply? Okay, so if I flip that up, I'm going to put the 3 on top, and then I'm going to put like -4 on the bottom. That fair? And then cancel, cancel, reduce, reduce, 1, 3, so you get 1/3. So that's what we got for the first two. But we'd have to check that the rest also give you 1/3, and I'm trusting that they do. So R would be 1/3 on that one. We still good? All right, now, the next problems, A, B, C, and D are for you, and I'll give you a second to try and figure them out. Now, remember, I haven't even told you this, but arithmetic and geometric are two types of sequences, but they aren't the only ones. It is possible to not be arithmetic or geometric. So look at these sequences, A, B, C, and D, and determine whether or not they're arithmetic, geometric, or neither. Because it is possible to be neither. And it is also possible to be both. You can be both arithmetic and geometric. So why don't you take a few minutes, and then we'll talk to each other if you need to. So if it's arithmetic, find D. If it's geometric, find R. Did anybody not get a copy of this? Okay. I have another one. I also have a sign-in sheet. You're supposed to, I guess, sign in that you were here. So I'll pass that around. There you go. I thought that was someone's ringer on their phone or something. No. If you have a question, just raise your hand. I'll come by and assist. When you're done, could you please just say I'm done? And that way I'll have an idea when most of you are done. Okay. I've only heard 3 dones. Oh, okay. All right. Okay, so how about A?
I say neither.
Neither? How many neithers? Okay, neither is correct. It's not arithmetic because it jumps by 1 and then by 1 and then by 2. So automatically you're done at that point. It's not arithmetic. Common ratio, you can do like 2 over 1, which is 2, but then you do 3 over 2, and that's not 2. So it's not geometric. So neither. How about B? Geometric, what's the common ratio? -3. Good. If you need me to work any of these out, like to show you, let me know. How about C? Both. Okay, if it's arithmetic, what's the D?
0.
0. It's jumping by nothing, right? Okay, and the common ratio is 1. Now, it's a rather boring sequence, but it is a sequence nonetheless. And how about D? Arithmetic. It is jumping by negative 1.5. So I think that's the first time that D was negative. You're actually decreasing. So you're subtracting 1.5 each time. We good? Okay, so the top of the next page is two formulas that allow you to find the nth term of an arithmetic and a geometric sequence. And I don't mind just providing you the formula and letting you use them, but I thought we might take a second to figure out why these formulas are what they are. All right, so, So think about this. Let's say that you have, suppose, this is the mathematical symbol we use for the word suppose. So suppose that you have a sequence, it's finite, it stops at m, and that it's arithmetic. I'm telling you it's arithmetic, and the common difference is d. Then the first number of the sequence is a sub 1. We all agree with that, right? The next one should be a sub 1 plus a d, because the common difference, I have to jump by d, right? So I take this number, I add d to it, right? Then the next number should be that first number, but it's 2 jumps, right? So plus 2 of the d's. And the third number would be, sorry, not the third, the fourth number would be the first one with 3 jumps. Make sense? So what we're trying to do is figure out what would the nth one be? Nth, not m, sorry. What would the nth one be? So this one right here, this is my second one. This is my third one. This is my fourth one, right? This one would be my fifth one. So my question to you is, what would the nth one be? So there's a pattern here.
A sub 1 plus.
So it should be a sub 1, and then plus,
N minus 1.
yeah, so notice if we wanted the fifth one, we actually had to do 4 d's. If we wanted the fourth one, we had to do 3 d's. If we wanted the third one, 2 d's. So if we want the nth one, we have to do n minus 1 d's. Do y'all see the formula? Okay, so I mean, if you don't see it, don't worry about it. There's the formula. You can have it and you can use it. You don't have to ask questions. But that's where it's coming from. It's the idea of the jumps, and you can, with relative ease, you can extract a formula from that. Okay? Do we care about doing the same thing for geometric to try and find it? I haven't done this, so let's do it. It's kind of interesting, right? No, maybe not. Okay, so let's suppose that we have the same story, except this is now geometric. And R is the common ratio. I need to teach 1440. I haven't taught 1414 in so long. I need to do it again. It's kind of fun. All right, so what are we doing here? This, if that's the first one, the next one should be, that's A2, yes, but it should be A1, but I had a common ratio, right, of R? So think about this. A2 divided by A1 has to be my R, right? That's right, because look, if I solve this for A2, multiply both sides by A1. And wouldn't you say then that A2 is A1R times R? So this right here is A1 times R. Make sense? That's our second one. And then now what would the third one be? Well, my third one over my second one should also be R. So A3 should be A2 times R. But what's A2? What's A2? We just found out what A2 was, right? This was A2? A sub 2? So A sub 2 is actually A sub 1 times R. But then I multiply by r again. So isn't it the first one times r squared? Do y'all see that? I know some of you do, and then I see some others that are a little lost. It's okay. I'm trying to create the formula. I know that's definitely not what I was told to do here, but I was just told to provide it. But I think life is always better when you kind of understand where it comes from, as opposed to just being fed a formula. All right, so let me put it down here. This one should be a sub 1 times r squared. That's our third one. So if we follow this pattern, the next one should probably be a sub 1 times r cubed, right? This should be our fourth one. You could just continue doing this. You know, do the fifth one over the fourth one, needs to be r, and then replace it. And like I said, if you're not following that, I don't want you to be all upset, all right? All right, now if I keep doing this, what would the nth one be? So I think I have almost the same pattern here, right? If I want the fourth one, I do r cubed. If I want the third one, I do r squared. If I do the second one, I do r to the first power. And all of them have a1 in them, right? a1. So times what? R to the n minus 1. And that's the formula that's provided to you. A sub n equals a sub 1 times r to the n minus 1. Right? That's what's here. All right. All right, let's see how we can use this. All right, part A says, if the first and 10th terms of an arithmetic sequence are 3 and 30 respectively. So they're telling us that a sub 1 is 3, and they're telling us that a sub 10 is 30. Do you agree with that? That's the information that's given to me. The first and 10th terms of an arithmetic sequence are 3 and 30 respectively. Yes? Okay. Then it's saying, find the 40th term. So it wants to know what a sub 40 is. We all understand that's the question, what's been presented to us? Now, we are told that it is an arithmetic sequence, right? We're told that it's an arithmetic sequence. So because it's an arithmetic sequence, we have a couple of things. One thing we have is that a sub n equals a sub n minus 1 plus d. That was the formula from the very beginning, right? And then we also have another formula that says that a sub n is equal to a sub 1 plus n minus 1 times d. So these are our two formulas that we have for arithmetic sequences, right? Those are two different formulas. So do you see any way that I might be able to use these to get that 40th one?
Like a sub n, the bottom one.
Use the bottom one?
Right, and then you would put a sub 40 is equal to a sub 1 plus 39 and d.
Times d. Okay, so I think I'm following you here. You're saying a sub 40 is going to be equal to a sub 1. Now we know what a sub 1 is, right? It's 3. If we do 40 here, then this number will be what?
39.
39. And then d is, well, we actually don't know what d is, do we? We're going to need to actually find d first before we try and plug the 40 in here.
The 3 and the 30.
So somehow maybe we can use this. So let's see. Let me try this. Would you agree that a sub 10, now I'm using a sub 10 because I know about a sub 10, don't I? Do you agree that a sub 10 using this formula is a sub 1 plus 10 minus 1 times d? You agree with that? Using this formula and this piece of information right here, I know a sub 10 is this. Now, I said using this information. I actually haven't used it yet. I'm doing a sub 10 because I know something about a sub 10. So what is a sub 10?
30.
30. So this is 30. This must equal a sub 1. A sub 1 is 3 plus 10 minus 1 is 9 times d. And now you have a nice little linear equation in d. You can solve that for d, can't you? What would you get if you solved this for d?
3.
So subtract 3 on both sides here. You get 27 equals 9d. And that would give you d is 3. So now we know what d is, yes? So d is 3. So there's this kind of like a two-part problem. We do that first. Now we can come back to this formula again. And I'll go ahead and replace a sub 1 with 3. And I'll box this up. This is kind of like my master formula now, right? Any general arithmetic sequence must follow this. The fact that I knew something about what was happening at the first number and at the 10th number, I was able to recover what d was. Once I know what d is for this arithmetic sequence, this is the formula that I can use for any term in the sequence now. Questions? So if I want to know what a sub 40 was, right? A sub 40 is 3 plus 40 minus 1 times 3. So I'm just replacing all my n's with 40s. So it should be 3 plus 39 times 3. And just make sure you do your order of operations correctly there. Is that 120?
Yep.
So don't be shy. If you have a question, please ask. You all right with it? All right. I imagine that the next part B is going to work very much the same, except that it's a geometric sequence, right? So that means these formulas that I can use are going to be different. Do they still want the same things? They want 40th, right? Okay. So what formula can I use to try and get this solution here for this, if this is a geometric sequence? Yep. Yep, I'm going to use this. Now the first thing I'm going to do is use this information to be able to recover what R is. Once I know R, I'm in business. I can find any term in the sequence, or any number in the sequence. All right, so I should probably put something like this. A sub 10 equals A sub 1 times R to what power? 10 minus 1, right? Which is going to be 9. Now replace everything. 30, 3, R to the 9th. And this is an equation with just the variable R in it, right? So I'll divide both sides by 3. Gives me 10 equals R to the 9th. Ooh. Yeah, so we have to get rid of the R to the 9th, so we take the 9th root on both sides. Hey, when you take the 9th root, do you have to do plus or minus?
No. Or, wait.
See, that's what I'm doing, right? I'm taking the 9th root on both sides.
No, you don't.
Do I have to do? I don't have to do plus or minus only if this is an even number. So if you take the square root, or the 4th root, or the 6th root, or the 8th root, then you have to do plus or minus. But if you take an odd root, you do not need plus or minus. So R is the 9th root of 10, or another way you could write that is 10 raised to the 1/9. This is called radical notation, and then this is your rational exponents. These mean the exact same thing. So when I'm on my calculator trying to figure out what this is, I do this. I do 10 my calculator, I do 10, then I use that little caret key, and then I do in parentheses 1 divided by 9. And that's how I'd figure out what that is, all right? But hold off on that. We don't need that yet. That was just to get R. So now let me go back to this formula, right? Let me go back to this formula. And I can replace A sub 1 with 3, and I can replace R with this, right? Okay. So this will be my master formula that I can use for this sequence now. It's A sub n equals A sub 1, which was 3 times, I'll do 9th root of 10. It just looks nice like that. All that to the n minus 1. This is the formula that I can use for this specific geometric sequence. And now I want the 40th one, right? So I'm just going to replace my n's with 40, and I'll be there. So A sub 40 equals 3, and then the 9th root of 10 to the 39th power. Okay, so I need my calculator. All right, I give up. This is 3 times, if you like, you can do 10 to the 39 ninths. That's what this means. When you raise something to the 39th, but then you take the root, it's the same as raising it to this power. But that's what I'm doing. I'm going to do 10 raised to the 39 over 9. Get that answer, and then multiply it times 3. Anyone want to share what they got?
1.216
I'm getting something else. Yeah, but you said you got 1 point something, right? 64,000? Yeah. Okay, 64,633. And I think it says to round here, right? 3 decimal places. So I think I would be going 041. I'm not quite sure how picky. Do you call her Mrs. Manchester, right? Okay. I'm not sure how picky she is about rounding, but let me see what she has on her answer key. Oh, she went 4 decimal places, so whatever. My whole theory is we're not trying to put a man on the moon right now, right? So I think we can be a little bit tolerant of decimal places, all right? Questions? So if you had to kind of summarize the last 2 examples, in order for you to figure out what's happening later on in the sequence, what did you have to know? Yeah, but to get R and D, what did you have to know?
You had to have at least 2 numbers of rings.
You had to have 2 pieces of the sequence, right? So any 2?
I would say
Any 2?
Which first thing you want?
I needed the first one, both all the formulas I used, right? Look at this formula we started with. Didn't I need to know the first one? Right? And in the previous arithmetic, I needed to know the first one. So I guess the big picture here is this. If somebody gives you the first number in the sequence and any other number in the sequence, you'll be able to come up with the formula for the sequence. But if they don't give you the first one, well, that would be a little harder, and it's not going to be asked. But I just want you to understand what was required for us to recover the formula. We needed the first one and some other one, then we can get any of them, right? Replace that with 400, and we can just do the same thing, place that with 400 minus 1, and we got it, right? But we had to have that first one to do it, and then some other one. All right. I don't know if I can show you the next 2 formulas or not. I didn't come in prepared to do it like I didn't even think I was going to show you where those other 2 formulas came from. Should we try or no? You want to see if we can figure out where the hell? I always cuss in my classes, but this isn't my class, so I can't. Sorry. I wouldn't say I'm like potty mouth, but I do get out of control sometimes. All right, so let me see here. 2a1. This formula looks terrible. Oh my gosh. Okay.